once thought to follow a predictable timeline beginning with the Big Bang. The evolution of our universe is now revealing complexities that challenge the very foundations of modern cosmology. With the powerful James Webb Space Telescope, JWST, probing the farthest reaches of space, scientists are encountering enormous, well-formed galaxies that shouldn't exist so early in the universe's history. They're also detecting unexpected fluctuations in dark energy and signs that time itself may not behave uniformly across the cosmos. These discoveries point to a universe far more intricate than we once imagined. At the center of these revelations lies dark energy, an enigmatic force named more out of mystery than understanding. Initially, scientists believed that gravity would gradually slow down the motion of galaxies. However, observations showed the opposite. Galaxies are accelerating away from each other. This surprising result suggested the presence of a repulsive force pervading the fabric of space, an idea that echoes through Einstein's equations of general relativity. In simplified terms, this force is modeled as a constant energy density filling all of space, commonly known as a cosmological constant. According to current models, dark energy makes up about 68% of the universe. Dark matter, an invisible substance that helps hold galaxies together, accounts for roughly 27%. The remaining 5% consists of ordinary matter, stars, planets, and everything familiar to us. The first major clue pointing to dark energy came from studying distant supernovae. Their light revealed that the universe's expansion rate is increasing over time. Observations of the cosmic microwave background, the afterglow of the early universe, have further supported this finding. However, new high-precision data from advanced telescopes and large-scale sky surveys are exposing cracks in this framework. Some measurements suggest that dark energy might not be constant after all. It could vary in strength over time or behave differently in various parts of the universe. This brings us to the Hubble tension, a growing discrepancy between two major methods of estimating the universe's expansion rate. One method analyzes a cosmic microwave background, while the other relies on observing nearby galaxies and supernovae. If dark energy were truly uniform, these two approaches should yield similar results. But they don't. This inconsistency has prompted scientists to consider whether dark energy changes over time, or whether our existing cosmological model is missing crucial elements. Another radical idea proposes that time itself may flow at different rates depending on the gravitational environment. The time-cape cosmology theory suggests that these variations in gravitational intensity could distort our perception of cosmic expansion. If time moves faster in the vast, empty voids between galaxies and in densely packed regions, our measurements might falsely indicate an accelerated expansion, mimicking the effects of dark energy. This wouldn't eliminate dark energy entirely, but it would reshape how we interpret the astronomical data pointing to its existence. Some researchers are now exploring whether dark energy could emerge from quantum fluctuations in vacuum space, or if it might be tied to dynamic energy fields, such as quintessence, that vary across time and space. These remain speculative, but are promising frontiers in theoretical physics. The JWST's unmatched ability to observe the early universe offers a critical opportunity to test these ideas. By studying the birth and distribution of galaxies across different cosmic epochs, scientists can determine whether dark energy has truly remained stable or evolved over time. If galaxy clusters form at unexpected rates, it could signal a changing influence of dark energy. To this day, dark energy remains one of the greatest unsolved mysteries in astrophysics. As the evidence mounts and our tools grow more powerful, we may find ourselves forced to rewrite key chapters of our cosmic story. As instruments like the James Webb Space Telescope, JWST, continue to gather increasingly precise data, our understanding of the universe, and particularly the enigmatic force driving its expansion, is being reshaped. Scientists may need to modify Einstein's widely accepted equations, or even propose new physical principles to reconcile the growing body of conflicting observations. One compelling alternative is timescape cosmology, a theory that seeks to address these foundational discrepancies without invoking mysterious energy forms. Instead of proposing a new force, this framework suggests that the perceived acceleration of the universe's expansion might stem from a misunderstanding of how time flows in regions with different matter densities. According to this view, galactic motion isn't driven by an invisible force, but distorted by the way we perceive time. If time flows at different rates in dense galaxy clusters compared to vast, emptier cosmic voids, our measurements may be misinterpreted, making distant galaxies appear to recede more rapidly than they actually are. This challenges a conventional assumption that the universe operates under a single universal clock. Mainstream cosmology treats time as uniform, estimating the universe's age at about 13.8 billion years. Timescape cosmology, however, argues that even small variations in time flow, when compounded over billions of years, can create significant observational discrepancies. Proponents of timescape cosmology suggest it may help resolve the Hubble tension, the current mismatch between different measurements of the universe's expansion rate. Instead of relying on a constant dark energy component, this theory attributes the apparent acceleration to the uneven curvature of space-time, shaped by the clumpy distribution of matter across the cosmos. Researchers are now comparing predictions to large-scale observational data, and some early findings show that timescape cosmology can match, or even slightly outperform, the Standard Model. Nevertheless, it remains a niche theory, partly due to its complex mathematical foundations and limited mainstream acceptance. Many astrophysicists caution against abandoning simpler explanations, such as the idea that dark energy may be dynamic or that Einstein's theory of gravity might need refinement. This doesn't imply a rejection of relativity, but rather a call to deepen our cosmic understanding, which may currently oversimplify a universe far more complex than we assume. For example, cosmologists often treat matter as evenly distributed on large scales and the universe as isotropic, appearing the same in every direction. Timescape cosmology challenges these assumptions, suggesting that such simplifications may obscure subtle yet significant variations. Ongoing investigations, especially those leveraging new JWST data, will be crucial in testing this model. If early galaxies appear unusually mature or display structures inconsistent with standard dark energy models, that could bolster support for this approach. Consequently, timescape cosmology joins a broader set of non-traditional theories seeking to reinterpret the cosmos and its rate of expansion. The JWST itself has already delivered breathtaking infrared images and spectra from the universe's infancy, igniting widespread debate. Positioned far from Earth, this telescope can detect light from over 13 billion years ago. Contrary to expectations of chaotic, primitive galaxies, JWST has revealed massive, well-organized structures, some with rotational symmetry and disk-like shapes. One striking example is the so-called Big Wheel Galaxy, a disk-shaped system that appears far more evolved than traditional formation models would predict for such an early epoch. Standard theory suggests galaxies should take much longer to reach this level of complexity. These observations raise two possibilities. Either our cosmic clock is miscalibrated, or galaxy formation processes are vastly more efficient than previously believed. This matters profoundly. The characteristics and distribution of early galaxies are central to our understanding of key cosmological elements, including the role of dark matter, the behavior of dark energy, and the mechanisms behind cosmic inflation. If galaxies were indeed larger and more mature in the early universe, it could imply that the cosmos is older than we currently estimate, or that its structure developed at a much faster rate. The discovery of heavy elements in ancient galaxies has deepened existing cosmological mysteries. Elements heavier than hydrogen and helium are forged within stars and disperse into space when those stars explode as supernovae. Detecting such elements in the early universe suggests that cycles of star birth and death occurred much sooner than previously believed, indicating an accelerated pace of cosmic evolution. The James Webb Space Telescope's JWST ability to observe ancient light is also reshaping our understanding of the universe's expansion rate. If present-day observations diverge from projections based on early cosmic light, it may point to an evolving form of dark energy, or even fundamental changes in our understanding of universal laws. However, some of these puzzling findings might stem from observational artifacts. For instance, exceptionally bright and distant objects could be misidentified as closer ones that simply exhibit very red light. To minimize such errors, astronomers employ cross-verification across multiple light spectra and use ground-based instruments to confirm distances. Yet the growing number of unusually massive galaxies detected at surprisingly early epochs appears too consistent to be dismissed as observational error. This trend has energized the scientific community, prompting some researchers to reconsider whether the Big Bang model, while still strongly supported by evidence like the cosmic microwave background, requires significant revision. The unexpectedly mature galaxies seen by JWST are already prompting updates to models of galactic evolution. One hypothesis posits that the universe's first generation of stars, known as population 3 stars, were enormous and short-lived. These stars could have rapidly enriched interstellar gas, catalyzing swift star formation. Others suggest that current galaxy formation simulations, which rely on cold dark matter and hierarchical merging, may be underestimating the speed or scale of early structure formation. Some even entertain the possibility that our distance calculations are flawed, although this alone is unlikely to explain all anomalies. Complicating matters further, the early emergence of massive galaxies overlaps with the mystery of supermassive black hole formation. Conventional wisdom holds that these black holes take time to grow, yet JWST data shows they may have formed much earlier than previously thought, further challenging established narratives. These revelations are pushing the limits of existing simulations and theories, spurring development of more advanced, adaptable computational models. At the core of these complexities lies a deeper possibility. We may not be perceiving time and space as they truly function. Cosmic voids, vast, sparsely populated regions of the universe, are gaining attention for their potential influence on large-scale cosmic behavior. According to timescape cosmology, these underdense areas might age faster than denser regions due to gravitational time dilation. Over billions of years, such differences in the flow of time could produce effects that mimic an accelerating universe. Importantly, these voids aren't truly empty. They contain faint galaxies and filamentary structures, but their relative emptiness could cause time-dependent phenomena to appear more advanced within them. Gravitational lensing, the bending of light by massive objects, might help scientists detect and measure these subtle temporal distortions. While the data is intriguing, it's not yet conclusive. What JWST and other cutting-edge missions may be revealing is not just new data, but the beginning of a paradigm shift. Our current models of galactic evolution, dark energy, and even the nature of time itself may require fundamental rethinking. These ideas aren't science fiction. They stem directly from principles in Einstein's theory of relativity, which teaches us that time is not absolute and that gravity warps both space and time. While skeptics argue for more conventional explanations, such as underestimating the pace of early star formation or misjudging cosmic density, proponents of timescape cosmology suggest that variable time rates across different cosmic regions could offer more cohesive solutions without invoking hypothetical dark forces. Regardless of whether these radical ideas endure scrutiny, they are expanding the scope of cosmological inquiry, mapping how matter is distributed across space and how galaxies connect within the cosmic web will help refine our understanding. Upcoming observational tools with broader scopes and higher resolution promise to shed light on the roles of voids, galaxy clusters, and the flow of cosmic time. One particularly intriguing development concerns the alignment of galaxy spins. In a universe born from random quantum fluctuations, galaxy rotations should be directionally random. Yet, large-scale surveys suggest a surprising pattern. A statistically significant number of galaxies seem to rotate in similar orientations. This phenomenon recalls earlier findings in the cosmic microwave background, where peculiar alignments, dubbed the axis of evil, challenge the assumption of a directionless, isotropic universe.